Hey gang, and welcome to another Worksheet Solutions walkthrough for the worksheet, Fischer Projections. Okay, so you know the drill by now. You've seen the topic of Fischer Projections. Most likely you've already watched the instructional video on jOeCHEM. You've looked at the worksheet attached with that video. Maybe you tried it. Maybe you looked at the answers, but you're looking for more. You're looking for more explanation. How did these answers get arrived at? Well, you, geochemists, are in the right place. This video, we're going to try to go through this worksheet as efficiently as possible. I'll show you how the answers were arrived at. I'll give you some deeper explanation, so hopefully you will get the answers you are looking for. So let's do it. Okay, gang, so tackling the first three problems of problem one, I just want to say before we start, remember with Fischer projections, right, when we see an intersection like this, we are really seeing, right, obviously we're seeing straight lines, but remember, the lines going up and down, they are actually going away from you. You can picture them as dashes. And the ones, on the sides, left and right, they're like arms coming out to hug you. So they're wedges, they're coming at you, right? And that matters when we're considering, assigning RNS configuration to stereocenters and identifying lowest priority groups and getting our conventions straight. So, I'm gonna erase this. So if we look at these first three, coincidentally, they are all S configuration, but let's see how that worked itself out. So if we see this stereocenter right here, right? We have these three stereocenters, and I will start with this and go to the right. Remember, nothing changes when we're assigning RNS. This is the OH, right? The oxygen is our first, heaviest, highest priority group. Then we have, oh, I apologize, no it's not. It's the chlorine, then it's the oxygen, then it's the methyl group. Where's our lowest priority group? It's this hydrogen. All right, so now we're in Fischer projection land, and since the hydrogen is on, one of these top and bottoms, it's facing away from us. So, do we have our convention satisfied? And yes, the lowest priority group is facing away from us, so we can just assign and that, do our molecular steering wheel, and that is actually what our configuration is, and we are turning to the left, and that's why we are S. Moving on over here. I'll get this right this time. Bromine is our heaviest group, followed by fluorine, followed by the carbon in ethyl, the ethyl group. However, right, even though we look like we are R, right, remember now our lowest priority group, the hydrogen, is on one of those left and right connections to our stereocenter in this Fischer projection, and that's coming at us. So we actually have to take the opposite. It looks like R, but it's actually S. Okay? Now, finally, over here, iodine by far is our heaviest group right there. Then it's going to be this isopropyl group over here because we do have a tie here between carbon and carbon, but this carbon is attached to two other carbons versus this carbon that's attached to three hydrogens. And then we have the methyl group coming in third. Now remember, we look like S, and our lowest priority group, the hydrogen, is facing away from us, so we are in fact S. So you can see how coincidentally these are all S, but how we arrived at that answer. So let me erase these, we'll do the last two, finish off problem one. Okay gang, so let's finish out problem one. So if we look at these next two Fischer projections, maybe we thought this when you did the worksheet, it's a little bit more difficult, but I promise you it's actually not. It looks like it, but everything is exactly the same. So if we take a look here, all you need to do is take it one stereocenter at a time. You just have to, so if we take this one for example, we just need to look at what's attached at that carbon, just like we would in any other situation when we are assigning RNS. So if we take a look here, bromine is our heaviest, atom right off of this carbon. Then it's oxygen, right? Because at this point, I have to consider hydrogen, which is easily our lowest priority group, or this carbon down here, right? And again, should we have had a tie, we can still play the game of what is that carbon attached to. We don't have to do it here. So we can say bromine's the heaviest, this oxygen in the OH, the alcohol, is second heaviest, then it's this big chunky thing down here, 3 right there. Okay, so we can then draw our wheel, which looks like it's turning to the right. However, our lowest priority group is facing us, so it's not R. That's why we have S. Okay? Hope that makes sense. So what I'm going to do is, just to avoid confusion, I'm going to clean up my numbers and start fresh with this asterisk carbon. Okay? So same deal. Nothing changes. look, we need to identify our highest priority group off of this carbon, and that's the chlorine. Because if we go up, it's carbon, and if we go down, it's carbon, but directly off of to the right, it's chlorine. Now here's where we have to break a tie, and where things get interesting. And I will use a separate marker for this. I'll use green. So up here, this carbon, right? Because if we go up here, we have a carbon, and if we go down, we have a carbon. So this carbon up here is attached to a bromine, an oxygen, and a hydrogen. So something pretty hefty right off the bat. Now if I go down here to this carbon is attached to a nitrogen, a carbon, and a hydrogen. So you can clearly see that this bromine trumps the nitrogen. So it's up, it's this way. That is priority number 2 for this carbon. And then down here is priority 3. Okay, I'll erase this. So, actually I'll leave that up here. So when we draw our circle, it looks like we are turning to the left. However, lowest priority group is facing us, so it's not S, it's R. Okay, so I hope this is making more sense if this was a point of confusion for you when you were doing the worksheet. So I will clean this up, and we will now move to this last stereocenter that I'm going to box. Okay? I'm just trying to do different things to the carbons so I can refer to them. So if we're looking at this square carbon now, this is a little bit easier, right? So right off the bat, what's the heaviest thing this carbon's attached to? Well, it's this nitrogen, right? Because remember on the periodic table, we go carbon, nitrogen, oxygen, fluorine. So it doesn't matter that this carbon up here is attached to a chlorine. Nitrogen right off the bat is heavier than carbon. So, but now, having said that, this carbon absolutely beats out this methyl group because, yes, the carbons have a tie here, but this carbon's just attached to 3 hydrogens. This one's attached to a chlorine, another carbon, and a hydrogen. So the methyl group comes in third. So if we draw our circle, it looks like we are turning to the right. However, right, lowest priority group, this hydrogen is facing towards us. So it's not R, we are in fact S. Okay, so that can be weird the first time you do it, but then afterwards you get like an example under your belt, a second problem, you're good to go. So let's tackle this over here. We'll start off same way, top to bottom. I'll dot this carbon. So, heaviest thing off of this carbon, no doubt, is the chlorine. Then it's going to be the oxygen straight away. And then it's going to be the carbon down here. So we didn't have to break any ties. So, lowest priority group is facing us, so we will assign and then take the opposite. So it looks like we are S, but in fact we are R. Okay? So I'm going to erase these to clean up. Now, this carbon down here that I'm going to asterisk, we have the iodine that is heavier than the bromine. Then we have the bromine, and then we're going to have to break a tie. So interesting, no hydrogen here. We've had hydrogens as our lowest priority groups. Now we're going to have one of our lowest priority groups be part of the chain itself. So if we go down here, we have this, I'll do my tiebreaker. So this carbon is attached to a carbon that's in the ethyl group, as well as another carbon that's down, and then a hydrogen. However, the carbon that's the dot carbon is attached to a chlorine, an oxygen, and a hydrogen. So clearly you can see this carbon up here wins. This is our lowest priority group. Okay, and I'm not going to label. We don't typically label the lowest priority group. So what I will do is I will draw my circle. It looks like we are turning to the left S. Lowest priority group is on the vertical, which means this is facing away from us. So we can actually just go ahead and assign and take that to be what it is. It's S. Okay. All right, clean up. Now let's go ahead and I will box this carbon, square it. So same deal. So actually now we just have a bunch of ties everywhere. We have carbon, carbon, and carbon. Lowest priority group being the hydrogen. Right, so I think it's easy to see this carbon up top is attached to an iodine, a bromine, and then another carbon up top. So this carbon's looking very strong to be priority number 1. And I'm going to go ahead and do this down here. This carbon over here, the ethyl, is attached to carbon and then 2 hydrogens. If you expanded it out, this carbon down here is attached to a carbon, carbon, and a fluorine. So fluorine, carbon, carbon. So you can see that this is first priority, this is second, this is third. So for the square carbon, we are turning S. However, lowest priority group is facing us, so we are in fact R. We need to take the opposite. And so those are the only three, and I was trying to be sneaky here, but this is deceivingly looks like a stereocenter. However, we're not attached to 4 different things. Methyl group, and then I just drew the methyl group slightly differently. Okay, that is problem 1, gang. So I hope you're feeling a little bit better about assigning RNS on Fischer projections, but let's go to problem 2. Okay, gang, so in problem 2, we just have 3 little subproblems where you just need to find the stereochemical relationship between the pairs that I've given you. So I'm just going to go up with the priority groups already labeled. We'll just assign RNS real quick, and then we will, label the pair. So obviously chlorine, then oxygen, then the ethyl group. Go 1, 2, 3. Lowest priority group is this methyl group. So even though we look like we are going R, we in fact need to take the opposite. We are S. And well, we look like we are turning R here, but lowest priority group is facing towards us given our Fischer projection standards. So again, instead of R, we are S. So given the fact that we have one stereocenter here, everyone's connected in the same way, so structurally we're the same. This is one of the situations where the relationship is, this is the same molecule. And I think if you even just take a second, I think you can see if you do a switch of this, and then once the OH is over here, you do a switch of here to here, you can see I was being lame, a stinker. I just did a double switch from here to here because I wanted to show you that you can very possibly be presented with a pair that ends up being the same molecule. So let's keep going. Okay, gang, second part of problem 2. So what I'm going to show you how to do is we're going to do the actual kind of assigning work here, even though I have it labeled, and then I want to show you how to save some brain power. So in this example right here, if we're going to take a look at this dot carbon right here, and if you ever see CHO, I know you're probably starting to see like more what I would call grown-up organic chemistry notation. This is an aldehyde and it looks like this. See, like that. So this is the only time I'm going to draw this out like this, but if you see CHO, just in your head, put an aldehyde in place of the CHO. Okay, so if we take a look here, right, for assigning stereochem at this carbon, obviously oxygen reigns supreme because that's directly attached to the carbon, and then we need to break a carbon-carbon tie here. What I hope you can maybe start doing in your head is this carbon is only attached to a nitrogen, a carbon, and a hydrogen. Now this carbon is double, it only needed to be attached once, but it's attached twice to oxygen. Oxygen outweighs nitrogen and carbon, so this is your second priority right here, that carbon. Then your third priority is down there, going down, literally. So if we draw our wheel that we would be turning, it looks like we're going to the right. However, our lowest priority group is facing towards us. Nix that. So instead of R, that's how we get S. So let me clean up here. That's the sound of cleaning. Okay, so if we take a look at what I'm going to do as the asterisk carbon, right off the bat, the nitrogen now reigns supreme because it is directly attached to this carbon. Nitrogen's heavier than carbon and carbon. So now we need to break a tie between these two carbons right here. So I think you can see that this carbon up top is attached to an oxygen, a carbon, and a hydrogen. However, this carbon down here is attached to an iodine, the first carbon in that ethyl, and then one more carbon. So clearly the iodine alone beats the carbon going up. So going down is second, going up here is third. So should we make our wheel, it looks like we're going once again R, however, lowest priority group is on the horizontal, so that comes at us in Fischer projection land, not R, but S. And one more time, why not? And then you'll see why I'm going through this. I'm not going to go through this the full way. I'm going to show you a shortcut. Down here, iodine, the heaviest, calling the shots. Over here, so then we have a carbon-carbon-carbon tie. This carbon up here wins. I could go through it, but I think it's pretty obvious why. Then ethyl wins, and actually our lowest priority group is on the vertical, so we can just assign and take that for what it is, and wouldn't you know it, it's S. Okay, so just a little bit more practice in doing that. So now, what I wanted to show you. So if we go from here to here, hopefully the only thing you can see, if we're just considering the dot carbon, the only thing that is different from here to here is there's a switch of the OH and the H, aka a single switch. So I don't even need to use my brain. I just know that it's S over here. I did a single switch. This is R. And please assign to check me, but that's R because there's a single switch. Then down here, again, a single switch, right? And I know it's about this carbon, and the only reason this is valid is because nothing else changed, right? It's the same structure above and below, but about this carbon, just the orientation of these two just changed. So it's S over here, it's R over here. And last but not least, I made it worse. Okay. Last but not least, we again see another single switch about this carbon. And I'll be consistent, square. I'll square this one over here. Iodine's still in place, but the only thing that's changed is the CH3 and the ethyl. Just a single switch, okay? So, with full confidence, I can say it's not S. This is R. And again, I welcome you do the assigning over here. But you'll see we have all S's here, we have all R's here. Because this is exactly opposite at every single stereocenter, we have ourselves a nice pair of enantiomers. So I will say this, make sure you're comfortable with assigning R and S, and you're actually comfortable and you're not just kind of, being a rogue cowboy, cowgirl about it. But if you can realize where there's just been a single switch, then feel free to save your brain power and assign one place, and then know you can just take the opposite in the next, or like if you have a pair of molecules or whatever. Okay, gang, last one of problem 2, let's do it. Okay, gang, end of problem 2, let's do it. So taking a look at here, so I think you can see right there some aldehydes present. Now I want to show you this real quick. This is kind of the shorthand you may see for a carboxylic acid. Again, I won't be expanding this out like this in the future, but just wanted to kind of give you a look as to what it is. You have a carbonyl, right, a C double bonded O, and then you have a single bond to the OH, the alcohol part of your carboxylic acid. So we're gonna we're gonna speedily go through the RNS assigning and then show you one little trick at the end that could have saved you some brain power. But here, first priority goes out to the oxygen and the OH. Then it's up here because this carbon is bonded 3 times to oxygen as opposed to the 2 times for the aldehyde carbon. So lowest priority group is this carbon down here. Didn't really even pose a threat. We look like we are turning our wheel to the right. Lowest priority group is facing away from us in this Fischer projection, so we are in fact R. Down here, neither of these two are really going to be the first things we're looking at, because even though we have tied carbon, tied carbon, tied carbon, tied carbon, right here, just by going to the first carbon, this carbon's attached to iodine. So right down here, this wins outright. Then second goes up here, and again, we are considering this carbon. Here, I'll go back to my old system. And then ethyl third, so our lowest priority group, the CH3, is facing towards us, so we need to go this way. We look like S, but we are actually R. Cleaning up. Okay, so down here, it is, and I'm forgetting a bromine down here. We have iodine, then bromine, fluorine, and then up here. So we look like we are R, and in fact our lowest priority group is on the vertical facing away from us, and we are in fact R. Okay, cool. So we could go through and assign R and S. I know you can do that. I can leave it like this, but my tip to you is if you just take this Fischer projection but look at it upside down, you might get to the R and S configurations faster. At this point, I'm very confident you can do this. I don't need to go through it. But remember, make sure you're comparing the correct stereocenters. Make sure you're comparing dot to dot, asterisk to asterisk, square to square in terms of the configuration, right? All I really did was draw this thing upside down and do a single switch on one stereo center, right? I left R is still R is still R, and it's just down here. If you look at this Fischer projection from this direction, or if you rotate it this way, you'll see all I did was flip the fluorine and the iodine. So we are not opposite at every stereo center. We are not enantiomers here. We don't have the same stereochemical configuration, so we're not the same structure, right? Because given the fact everyone is still attached, structurally we're the same here and here. We're just arranged differently. So we are diastereomers. Okay? So that does it for problem 2, gang. I'm sure by now you are stereo center assigning, configuration assigning pros with Fischer projections by now. The last thing I want to do in this worksheet is just take Fischer projections and do bond line, or vice versa. I kind of forget. Both. We're doing both. Problem 3. Okay, gang. Problem 3, 4 parts. Let's do it. So I'm not gonna lie, this conversion of Fischer projection to bond line, while some teachers may not even ask you about it, I just wanted to include it because it can be really kind of brain turning, brain cramping. But I promise you, once you kind of see it, you got it. So if we take a look here, the way I usually approach these, we're gonna go from the Fischer projection to the bond line structure, right? So, zigzags and wedges and dashes. So if we take a look here, the nice part is never freak out, because this is only a 1, 2, 3 carbon chain, or 1, 2, there's not that many carbons in it is what I'm trying to say. And remember, what I like to do is I like to start at the bottom, from the Fischer projection to the bond line. Now, don't forget, these are facing towards you. These are going away from you. So what I like to do is we are kind of looking at this from a bird's eye view right now. So here's what I like to do is I like to think, okay, the methyl group is on my left, the hydrogen's on my right. I need to take this where I'm looking at my paper, at my board, and I need to apply it in this plane. So I hope you're seeing that. Hydrogen's on my right, methyl's on my left. When I turn here, I hope you're seeing is that the hydrogen's coming at you, the camera, the CH3 is going away. So, hopefully you can see this. If my eye is looking down here at this carbon, like it is right here, this dot carbon, like I showed you, hydrogen, CH3, this hydrogen's coming out of the plane of the page, that is a wedge, and this methyl group is CH3 going through the plane of the page, right? Because this hand, that was the hydrogen's coming at the camera. And again, this only works because at this particular dot carbon, right, we are looking down on it, and this is facing away from us, this is facing away from us. And what does that eye see? This is going down, and this is going down. So I hope you're seeing that's kind of how this works. Now here's maybe the more confusing part. Now we need to kind of chain this. We need to go up one more carbon to this carbon right here to finish this structure off. So we drew this carbon right here. However, we need to kind of alter our perspective. We can't keep our eye at this position. So this is kind of gone now. We need to kind of have an eye that looks like, oh man, of course I can't even draw an eye properly. That's looking like this. Oops, sorry. So we need to, get into a perspective that sees this line going away and this line going away from itself. So I hope that you're seeing is if I just continue this, right off this line right here is this OH. This eye sees this going away from it as well as this going away from it. I know it's kind of going, this way towards it, but it is going up and away. So now what we need to figure out is where does this eye see this CH3 and this hydrogen? Now, I like to use my hands right here. So I'm going to do this, but I need to now, instead of going like this, because the eye was going this way, I'm going to go like this. So the hydrogen's over here, this CH3, which I'm going to draw in, is right over here. And if I go like this, the H is now facing you, the camera, so this H is now a wedge, and dashed here, going through the board, CH3. I know that's weird because you kind of have to do that in a desk if you ever have to do this on an exam, but that's how I like to rationalize this. I kind of like to think, okay, I'm now looking at this and I know my eye is going like this. I'm turning this way. H is going out of the plane of what I'm writing on. The CH3 is going into the plane of what I'm writing on. And then we know we had this perspective. So H is going out of the plane. CH3 is going in. So dash for the CH3, wedge for the H. But hopefully if we do 3 more, it'll feel more natural. Okay, gang, let's do the second part of this problem. So if we take a look here, let's again start at the bottom. So we know we're looking at this carbon from a bird's eye view where this is facing away from us, the bromine's facing away from us, these two are facing towards us. So the very first thing I can do is, I know my eye is going to kind of be at this perspective right here. So let me have my dot carbon. Bromine's down and away, and so is the rest of this chain. I'll make that my square carbon. Okay? So now I need to think to myself, now what does this eye see as far as this CH3 and this hydrogen? So I like to do my little wings. So CH3 is here, H is here. So I'm going to turn to the perspective of the eye, which is this way. H is towards the camera, going out of the plane of what I'm writing on. CH3 is going into it. H is a wedge. CH3 is a dash. Okay? So now we have the square carbon. And what's nice is you can just fill in the rest of the chain. You know going up is just the aldehydes. You can go this way, CHO. And now you know this eye must be looking at it. Sorry if my eyes are creepy. I'm not a good artiste. And from this perspective, so if we're looking at this perspective, right, figure out H is on my left here, OH is on my right here. I need to assume the position of the eye. So OH is going into the board, H is coming at you all, the camera, out of the plane of what I'm writing on. Wedge is the H, dash is the OH. So I hope that's making more sense to you and how that works. It's kind of like you need to just adjust your perspective and you need to kind of have an idea of what side a group is on the Fischer projection and turn, either to the right or to the left, okay? When you're going from Fischer to here, and I hope you'll see that going from this to Fischer is just as easy. Part 3. Okay, gang, part 3. So we're going to go from a bottom line structure to a Fischer projection. So the one thing I want to do is you can see that, kind of in these terminal ends, not much going on. We're kind of, our challenge lies with those cross sections, right, where we have a carbon that's attached to 4 things. So what I'm going to do is I see kind of these 2 positions being those types of, intersections. I'm just going to fill in the hydrogens I have here, just to make sure I'm viewing everything before I get started. And in case you're wondering, the D, this D is deuterium. It's hydrogen with a second neutron. When you have deuterium, it's not like hydrogen. You can't just leave it off, not implicitly drawn. You have to draw deuterium. It's commonly included to do stereocenter stuff because it counts as a different group, and it's slightly heavier than hydrogen. Okay, so again, I like to start from the bottom. So let's make this the circle carbon, let's make this the square carbon. So we have the circle carbon, and what's super nice is remember, if this is the circle carbon, right, and this is down, away, given what we know about Fischer projections, right, this is my bottom and top. So I have a methyl group down. I'll even draw it like this just to make sure it's super obvious what it is. And then I have this square carbon going up. So up from here I have my square, okay? So my last challenge is to figure out the hydrogen in the deuterium. What's on the left and what's on the right? So what I like to do is I kind of like to think I'm this eye looking down. So if I'm looking down like this, the hydrogen is into the plane of the board, my left arm, and the deuterium is coming out of what I'm writing on towards the camera, my right arm, and then just do the opposite of what we were doing before. Turn to the Fischer projection you're drawing. Hydrogen's over here, deuterium's over here. And I truly think that's the simplest way to explain how to do this. It sounds so silly, but it makes it so easy. It gives it a process, because sometimes with this spatial stuff, you get freaked out because you can't see it, and you're like, I don't know how to do it. But if there's a process and it's reliable, then, for me personally, I always feel peace of mind when there's a process. Okay, so now we need to do exactly what we did before. We need to shift our perspective. So from the square, we already have this part down. So again, on the vertical, going away from the I, going up, is the aldehyde, the CHO. So now we need to figure out what's on the horizontal, what's on the left and what's on the right. Where are the bromine and where is the hydrogen? Where is the bromine, where is the hydrogen? So if I then take on this perspective right here, hydrogen is my wedge coming out at the camera, bromine's going into the plane of what I'm writing on. Let me turn to my Fischer project. Oh, wait, I forgot. Hydrogen's my left arm, bromine's my right. Hydrogen, bromine, and it's that simple, gang. Okay? So it's all about making sure you're positioning your perspective to make sure you're abiding by the Fischer projection rules. You shouldn't be, when you're looking at something, you know, the chain, I would say, needs to be going away from you, away from you, away from you, away from you. And then you can use your left and right arm to fill in the left and right on the Fischer projection. Last one, let's finish this worksheet strong. Okay, gang, so for the last one, of course, I had to give you a longer chain than what we had been previously dealing with. So if we take a look here, I even set this up for us a little bit. We have, you know, I would say call them intersections. We have 1, 2, and 3. So what I want to do first is we see this Fischer projection will turn into a 1, 2, 3, 4, 5. So there's a 5-carbon chain. We're in a Fischer projection where we have one intersection here, an intersection here, and an intersection here. So we can even fill it in, fill it in, fill it in, and you can see, given the chain 1, 2, 3, 4, 5, that means we have 1, 2, 3, 4, and 5. So, and these are just CH3s, right? Nothing special on the ends. So really, by doing just this, we've done most of the work. We have to just change our perspective in different situations to see where these groups are as far as left and right on the Fischer projection. So if we take a look here, I'm going to get on my tiptoes and go down like this. Fluorine is going through the board, that's my left arm. The OH is coming out of the board, out of what I'm writing on, towards the camera. I change. OH over here, fluorine right there. Now I'm going to go down this way. Going out of the plane of the board is the hydrogen. Going through the plane of the board is the chlorine. Now I will go here. Chlorine's here. Hydrogen's there. Last but not least, I'll do this perspective one more time. The NH2, the amine, is coming out of the board, coming towards the camera. The H is going through the board. I shift over here. NH2 is here. H is here. Gang, I hope you feel so much more confident about Fischer projections. I know some professors, some teachers don't throw them in stereochem, but they will definitely come up if you do carbohydrates in OCHEM 2. So I like this video because it works in OCHEM 1 and it works in OCHEM 2 as far as your Fischer projection fundamentals. If you're watching this video, that means you've donated some money to jOeCHEM, and I can't even express my gratitude and say thank you enough. Thank you for using jOeCHEM as your tool to conquer carbon. I'm so blown away that you have chosen jOeCHEM, and I hope to see you all in the next video.